And I think Professor Mimura will like these results as well. I'll talk in terms of Ligroups, but unless, does everybody know about H spaces in the, no? No? No, okay, good.
There are some algebraics, so they might not be familiar with.
Well, okay, all right. Well, I'll speak in general terms, but let me talk about Ligroups, I guess. So we'll have G be a, say, a topological group. And you should just simply think of your favorite topological group. Okay, so that's really the easiest way to do this. And of course, what I mean by this is that I have some multiplication defined on the group, and furthermore, I have. Let me form the following thing: G, one point union with. With itself, this is the collection of all things E with G or G with E, and there is a mapping of this to G called the fold map, which is simply if you have this, take G, and if you have this, take G. So that's the fold map. If I think of this as contained in G cross G, then this diagram now commutes. And so this is simply the condition that is written in more homotopical terms for the existence of an inverse, right? So you have some base point for which this mapping is commutes. So there are lots of other diagrams that are of interest that you can associate to a group like this. For example, the condition of being associative is given by the commutativity of this diagram. And however, the diagram that I really like, that's most interesting here, is the following. Suppose I take G and I map it, G cross G, and I map it by the diagonal mapping to G cross G cross G cross G. Let's twist around the middle terms, and then let me now apply the multiplication here. I'll go by the multiplication down to G and go over here by the diagonal map. So all I've really written down here is that if I take A and B and I map it to A, B, B, which I map to A, B, and then take E, B times A, B, then this diagram commutes. So there isn't any real great surprise there. However, what I've done by introducing these maps is show you the way in which the diagonal mapping interacts with the multiplication under these circumstances. So if I were to do all of this more generally, that is up to homotopy, then I would be talking about a sort of a homotopy version of a topological group, and that's what you would call an H space. But just think about your favorite Lie group and I assume everybody has a favorite Lie group. So now the diagonal mapping. Well, first of all, of course, we have that the Pontryagin product on the homology of G, which is simply the mapping which is induced by the product mapping. However, there's also part of the structure that comes with homology for free is the structure of the coproduct. So we have, in this case, two mappings. One multiplies and one unmultiplies. And so what this diagram is telling me is that that the coproduct is an algebra mapping. Did I get that right? Yes. So, so this extra piece of information that this structure, which comes for free, as I said, interacts with this special structure. That interaction is can be recorded by this piece of structure, and so together, if I put all of these things together, then I get a special structure, which is that of a Hopf algebra. So to make a much longer and more nuanced story short, a Hopf algebra is an algebra which is a coalgebra for which the coalgebra mapping is an algebra mapping. And of course, the algebra mapping is a coalgebra mapping. And all of these structures get along together. And in some sense, anything which has too much structure, well, there just aren't that many of them, you know. And so one of the beauties of having a great deal of structure is that classification is possible, and under certain circumstances you're able to write down nice forms for things. So
there is any relation between mu and delta star, or mu star and delta star?
yeah, well, I mean, based on this, for example, I get that that this commutes with the algebra structure, and then because it's a space mapping, I get the other way around too. Yeah.
Do you include the existence of antipode as a part of axiom, or?
I don't in this particular discussion, though those exist in this case as well. So, and they are.
Algebra is what sometimes some people call bi-algebra.
That's right. That's right. So I would, for this discussion, I'm only interested in the bi-algebra structure. Okay. But it's certainly the case that the antipode plays a role in other discussions in which one's doing topology as well. So, so I have in such Hopf algebras, I have I have one. There is a duality, and namely that if I take the cohomology of G, the dual space of this, then I have an algebra structure which is due to the diagonal, which is, of course, the cup product. And I have a co-algebra structure, which is the map induced by the multiplication. And this is also a Hopf algebra. So there is, well, there are indecomposable elements. Okay, with respect to the algebra, so if I take Q of H, this will be H modulo H times H, if I can use that. So let's see, I won't put a star on it, so you don't know whether it's homology or cohomology, but that is take the, and I've put a reduced sign on it that I'm not interested in the unit. Of course, there's a unit and co-unit in a Hopf algebra, but I think this is meaningful. These are the things which are not the expressible as products. Okay, so I have indecomposable elements, and then dually we have primitive elements. So I'll write this as prim H. These are X and H such that delta, the co-product on X is given by X tensor 1 plus 1 tensor X. So these are general things which you can associate to a Hopf algebra, and which I'll be interested in talking about. So this brings me to one of my favorite arguments of all time. So first of all, let me point out that if H is a Hopf algebra and H is commutative, and H is an algebra over Q, then we have one if H is generated by one element, X in an odd degree, then H is isomorphic to an exterior algebra on one generator. And 2 if generated by one element in even degree, H will be isomorphic to a polynomial algebra on one generator. Now, if it's generated by one element, of course, that element has to be both primitive and indecomposable, because it doesn't have anywhere to go or anybody else to keep it company. So what's interesting to see here is if you look at the diagonal applied to a power of X, then you get following formula, which is simply a generalization of the binomial theorem here showing up in the in the coproduct. So so what's a consequence of this? So this is a theorem of Hopf's from 1941. This paper appeared in the Annals of Mathematics, but it had been submitted to Compositio Mathematica, the journal that Brouwer had established, and because of the wartime, it all got lost. So somehow Hopf got it out to the United States where it could appear in the Annals. It's a very interesting history just to that paper alone. So here's the theorem that so if G is a finite-dimensional Lie group, then the cohomology of G with rational coefficients is exterior on generators of odd degree. So in some sense, this is a very satisfying theorem because it tells you that that if you're looking at the cohomology of a Lie group, then the choices of the algebra structure are very well constrained. I'm sorry?
Coproduct structure. That's how we define it.
It's a little more complicated but I'm establishing this as an algebra structure.
So when you say this Hopf algebra is commutative, it's just commutative in terms of
The cup product in this case. So this you get for free. It's graded commutative in technical sense, right? So, but the commutativity here is coming from the cup product being commutative. Yeah. So the proof of this is partly has to do with the proof of this fact over here, that if something is generated by a single generator, it has to be a polynomial in nature. So what I do is let's let the let's see, these are the indecomposables, which I'll think of as some vector space over Q on generators in various degrees. And let's let xk be the first even degree generator, and let's let AK be the sub Hopf algebra generated by x1 up to xk minus 1. And what I'm doing here is I'm setting up a situation where I can make this into primitive generator. So if I look at this exact sequence where I take AK, map it into the H star here, and then map into the quotient. Quotient of Hopf algebras is slightly trickier to define than you would like, and it's denoted in this funny way, but think whatever you think is right there, and take that as your definition. And so in here, xk is primitive. And the reason for that, of course, is if I take the coproduct on this, if it has any cross terms, the cross terms have to be in lower degree and hence have to be in A sub k. Now, if x sub k raised to some power t is 0, then, well, 0 will be what you get when you apply the coproduct to 0. But of course, if I apply the coproduct to this power, I'll get t sub L, t choose L, xk to the t minus k tensor, x, oh not, minus L to the L. And notice that the thing on the right contains expressions. If I take, for example, t to be the smallest height where this vanishes, then many of these things that are added up will be non-zero, and of course this is a contradiction. So therefore, the condition that xk raised to the t power is equal to 0 has to fail. But of course, if the Lie group is finite dimensional, then its cohomology has a highest degree, and the higher and higher powers of such an xk would exceed that degree, and hence have to be 0. So so the upshot is there can't be a first even degree generator, and then of course then it follows that I have an exterior algebra. So this is a very famous theorem. I'll just point out, by the way, that the Euler characteristic for this is 0. Just because it is, right? It's fairly obvious what the Poincare polynomial for that is, and when you evaluate it, you get 0. Well, Hopf was quick to point out that you got that Euler characteristic from that, because then all kinds of fixed point theorems can be obtained when you know the Euler characteristic, because the Euler characteristic is the Lefschetz degree for a self map, and that's homotopic to the identity, and so all kinds of things follow from the vanishing of this that are among the things that we don't learn much of anymore, but of course Hopf knew about and was interested in. So just put a plug out there for fixed point theory being interesting. Well, so here's a question. What about mod p coefficients. Well, here's an interesting simple observation, which is if I take the my binomial theorem over here, of course I'll get k greater than or equal to 0, choose k, x to the k tensor x to the p minus k, and now one uses the obvious fact that the binomial coefficients vanish unless k is 0 or k is p, and so in fact this is equal to x to the p tensor 1 plus 1 tensor x to the p mod p. And so if x is primitive, so is the x to the p. And it's also the case that when I plug this into this formula, I don't get a contradiction. Right? If x to the p is 0, then of course I get 0 on the left, but I also get 0 on the right. There are no terms in between that get in the way. And so it's possible then, we can have Hopf algebras that are small mod p. So in particular, if I take the polynomial algebra on an even degree generator, then I can mod out by the ideal generated by x to the p, and this has a perfectly consistent Hopf algebra structure if I denote x to be a primitive. So it's possible to make Hopf algebras mod p which are small and hence don't violate the finite dimensionality situation. And so then one starts to wonder, what's the cohomology mod p of various Lie groups, and are there factors like this that appear? I feel a little nervous saying this in front of Professor Mimura, who has shown the existence of many of these beautiful things in very deep calculations that he's done. But I'm going to forge ahead here and talk about these. So I would like to know more about these things, and I would like to know more about them in the following context. A simple spectral sequence. So this is by far the, in some sense, the simplest spectral sequence that you can construct. So let's consider the short exact sequence. Zero goes to the integers by multiplication by p, where p is a prime, and the quotient here, which I'll denote by the field of p elements, is so this is a very well-known short exact sequence, and this leads to an exact triangle where here I'll put, let me denote without anything h star of x to mean the integral homology. And so I have the times p mapping here, and then I have reduction mod p mapping down to the homology with coefficients in fp. And I have here a boundary mapping. And if I look at the induced mapping, which goes take the boundary and then reduce, then this mapping here, usually denoted by beta, and that's the Bachstein homomorphism. So the Bachstein homomorphism then leads to a, this is D1 for a spectral sequence with E1 equal to the homology of x with coefficients in the field of p elements. And then, of course, one has to ask then, to what does this converge? And this is converging to, let me write this down more carefully. This is going to be converging to h star of x. That's my D mod mod torsion tensored over fp. So when I think about the torsion in the homology of a space, of course, it's a very interesting set of things to be considering. If I have torsion at a different prime than p, then of course it will not figure in any of this. In particular, it won't be noticed by this homology here. And so, this number here is obtained. This, in some sense, is the dimension of the rational homology of x. So this is a very interesting spectral sequence. This spectral sequence is singly graded. So we don't have to do anything but put one grading down here, and the Bachstein, in this case, decreases degree by 1, and that's the whole story. So so one would think, well, aren't we really just talking about all kinds of well, long exact sequences, really, is what this is doing. Is there any purchase value in thinking about this construction as a spectral sequence, except that we can? So so let me tell you. So some of the interesting facts about this. Stop me if you have any questions, by the way.
With this spectral sequence, it tells you about the Betty number of this X space X.
That's right. That's right. That's right. So actually, you get the following interesting inequality. The dimension of the qth homology of X with FP coefficients will be greater than or equal to the dimension of the infinity term here, X mod torsion tensor FP over FP, but this is equal to the dimension over Q of should be Q HQ X with Q. So so there is a direct relationship, and furthermore, if this is a strict inequality, then there is torsion in P of order P in the homology of X. So teasing out exactly what the spectral sequence is doing at higher stages is possible by using intermediate short exact sequences of coefficients here. I put the kind of global case up here, but you could have mapped Z mod P into Z mod P squared with Z mod P as a coefficient, or Z mod P squared to Z mod P squared by multiplying by P and getting that as a quotient, and then sticking those things together, you obtain what you would see at the first stage of this. And so there's a very easy set of analyses for this, because when you look at what's happening to the D's in the exact triangle, you're getting elements that are persisting under higher and higher powers of multiplication by P, and so these are elements that survive and are expressible as P to some high power of something. So this is about, well, clearly about torsion. So here's the following theorem, which perhaps comes as no surprise, that if, say, G mu E is a Ligroup, then the Bachstein spectral sequence for H star G FP is a spectral sequence of Hopf algebras. That is, each term in the spectral sequence. So let me change the notation slightly from E to B for Bachstein. So B1 star, which is this. This is already a Hopf algebra by the fact that it's a Lie group, but I then take the homology of this with respect to the Bachstein operator, and this inherits a coproduct and product which interact correctly. For this to be a Hopf algebra, and then similarly, as you go down the line throughout the Bachstein spectral sequence, at every stage you have a Hopf algebra, and you have also a differential that respects the Hopf algebra structure. So that's, in some sense, no surprise, but at the same time, structurally quite a boon. It means that I can talk about primitives at every stage. I can talk about indecomposables at every stage. I can talk about having fewer differentials because the differentials all have to satisfy the structure. And I can even, and this is probably one of the wildest things you can do, you can take a Hopf algebra and you can filter it by, say, powers of the primitives and get a filtration of that. And the quotients of that will be simple Hopf algebras, and you can then show that the differential induces mappings on that and be able to get a spectral sequence which goes from a stage in the spectral sequence to the next stage in the spectral sequence. So now I have a spectral sequence to calculate from the first to the second term of a spectral sequence, and then I have another spectral sequence which goes from that to the next step. So you can interpolate infinitely many spectral sequences between each spectral sequence. All of this for a singly graded object. It's really quite odd in some sense, if you like. But once you have these structures, then you can imagine doing things like that. Well, let me tell you what's possible in this setting. So let's suppose that X is some even degree element in the B1 term. So this is some element of the homology mod P, and X is primitive. Okay, so delta X is X tensor 1 plus 1 tensor X. So I'm going to say that then let's say this. Okay. Then, if there is an element x1 in B1 to n times P with either x1 is x to the P. Remember that if it's x to the P, it's primitive. Okay. Or and this is not 0 here, by the way. I want this to be not 0 too. Or, and this gets technical, there is an element x bar in, notice the switch of the indices. So I've changed from the Hopf algebra given by B1 to the dual Hopf algebra. Okay, so this is from homology to cohomology. So some cohomology element. With the Kronecker product of the dual space, if I evaluate this functional on X, I get something non-zero. And if I take this and raise it to the pth power and evaluate it on my X1, I also get something non-zero. Then we call X1 a 1 implication of X. So, so that's definition of a 1 implication. A 2 implication would be a 1 implication of X1. And an infinite implication would be a list of elements starting with X and then X1, X2, X3, each one of them a 1 implication of the previous. So let's note that the degree of X1 is p times the degree of X. So these implication elements that I'm introducing each are growing in a family of elements that go higher and higher and higher in degree. So here's a theorem which is due to Browder. Which I think is an amazing theorem. If X in B2n is primitive, and X is equal to D1 of Y, it's all not zero, then X has infinite implications. That is, there's X, X1, X2, X3, where Xi plus 1 is 1 implication of Xi. So why? Well, first of all, let me discuss briefly why this is the case. But let me discuss first the implications of this. If I started out with, say, a finite dimensional Lie group, then, of course, the homology of G will be bounded above in some degree. And so if I look at the degree of this element has p times that degree, p squared times that degree, p cubed times that degree. And of course, it would eventually be past the possible degree, and therefore such a system of infinite implications cannot exist. And since it cannot exist, then the torsion, which occurs in the homology or cohomology of the Lie group, cannot occur in such a way that this is satisfied. And so one gets then that even degree generators are not Bach-Steins of lower degree things. And that leads to a very strong restriction on the relation between the rational data and possible introduction of elements into the homology of or cohomology of the various Lie groups. I guess if you, so let's take an example here. If I look at the cohomology of the exceptional group F4 with mod 3 coefficients, this is an exterior algebra on X3, X11, X15, and X23. Oop, that's the rational. Sorry, that's the rational cohomology. And if I look at the cohomology with coefficients in degree 3, or in prime 3, then there is an 8-dimensional generator that whose cube is 0. And I also have here X3, X7, X11, and X15. And in order to see the relationship between these, first of all, notice that first I cannot have a Bach-Stein originate on the 8th degree. Let me point out I'm doing cohomology, right? So it's the opposite condition here. I'm looking at the Bach-Stein on X. So the Bach-Stein on X will be 0, but since that obviously doesn't live to the rationals, it has to be the Bach-Stein of something, and so I get the Bach-Stein of X7 is X8 here, and you can see if the Bach-Stein of X7 times X8 squared will be X8 cubed, which is 0. And so the 23-dimensional generator is in fact represented by the class of X7 times X8 squared that lives to the infinite term in the Bach-Stein spectral sequence. So I won't say much about the proof of this because it's a lot of diagram chasing. But I want to mention an application of these results that I came upon that I think kind of give a different flavor to this. And so let me introduce the following. Let's let M be a complete compact Riemannian manifold. So complete means that if you give me a pair of points, there's some geodesic joining them. Compact means what it means. Riemannian is is what I need to have a geodesic to begin with. And so let me let n pq lambda be equal to the number of geodesics on M joining P to Q of length less than lambda. So I guess the right example to think of on this case would be to think of the round sphere and just take a pair of points. You can even take antipodal points if you like. The geodesics are great circles, and so what you're doing is you're counting up the number of great circles that you can get to go between North and South Pole, iterating that, of course, you have to add 2 pi every time you go about. So I have this value, and so this is the theorem of Gromov, which says that there is a positive number C that satisfies this condition that n pq lambda is greater than or equal to the sum k equals 0 up to c times lambda minus 1 of the dimension over k of the homology of the base loop space of the manifold with coefficients. I'm sorry, this should be too many k's. Into L. There we go. Now notice that in the case of a sphere, the homology for the loops on the sphere, you take the n+1 sphere, then there's dimension. Loops on the sphere will be dimension n, 2n, 3n, 4n, and so this sum will accumulate very slowly as you go upward, but that, of course, is consistent with once you join the north to the south pole, you need to go at least 2 pi more to get another geodesic to join those, and you go round and round and round like that. Actually, I'm sorry, the antipodes are bad. Take a point on the equator and the North Pole. And that way you get the 2 pi thing to happen. So Serre proved, using the Serre spectral sequence, that in fact the homology of the base loop space for such a manifold is non-zero infinitely often. And so that implies that this function grows linearly in lambda. But Gromov conjectured that, in fact, this function grows exponentially in most cases. So here's a theorem that tells you a little bit more about this situation. So,
I mean, you said this is function. This is a function of what? SPQ.
So
is it a function of lambda or a function of
it's
what
well,
variable?
you choose your 2 points P and Q, and then you allow lambda to vary. Right.
So it's a function of lambda.
Since the manifold is complete, the up to homotopy, the set of all paths joining P to Q is in fact the base loop space at P. So you simply just move Q along. any path joining it to Q. And so, so really I'm talking about Morse theory on the space of paths between P and Q, and the space of paths between P and Q is simply the bit up to homotopy, the base loop space. So, so in some sense, this is a Morse theoretic result. The Betty numbers for this, with respect to the field K, are forcing the analysis to satisfy this inequality. So here's our theorem. This is due to Sullivan for the rational field, and for me for K equals Fp, and that is if the cohomology of the manifold M requires dimensions over K of the homology of the loop space on too many K's. L equal 1, 2, 3. These dimensions is an unbounded set. So the dimensions grow larger and larger and larger. So,
They are algebra over K, or?
yeah. So if you can find, let me give you an example of this. If I take the two frames in odd dimensional, so this is the Stiefel manifold. If I look at this rationally, or I look at it mod an odd prime, this looks like a, I think, 4n plus 3 sphere. Maybe it's a 4n plus 1 sphere. 4n plus, yes, 4n plus 1 sphere. This looks like a 4n plus 1 sphere. But at the prime 2, it looks like it has two algebra generators, which are linked by a Boxstein, whose product is this. So this is an example of a manifold for which you need F2 data in order to decide this. Well, let me tell you what went on here. The proof of this for Fp goes like this. I'll assume that rationally it's not true, that these are all bounded by something. Then Sullivan tells me everything I need to know about that. And so if that's the case, then Sullivan also showed that if this requires at least two algebra generators over Q, then it would be unbounded. So that must mean that this requires only one algebra generator. If mod P it requires two, then something has to happen in the Boxstein spectral sequence for those generators to go away, and only one of them to remain. So I know that the Boxstein spectral sequence on this has a non-trivial play, which then I can lift up to here to get a non-trivial Boxstein to occur on this. So now over Fp I have some residual data from the rationals, if I'm lucky, and then I have something that gives rise to infinite implications. The infinite implications if I put all of them together, they form a Poincare series that looks like a polynomial algebra. So now I have two polynomial algebras in a Hopf algebra, and so all of the products between those things all multiply together, and I end up with an unbounded set of numbers. In the case that rationally this thing vanishes and rationally this vanishes, then I have even more Bach-Steins to play with because I have two algebra generators here, and so some simple Serre spectral sequence arguments allow me to find two, once again, two different families of primitive, infinite implications, and those give rise to these unbounded degrees. So this I found to be kind of an unusual thing in that implications were designed to produce elements so that you could show that they weren't there. And in this case, infinite implications can be used to show elements are there in abundance, and that abundance leads to nice differential geometric consequences. And all of this is all legislated by the structure of the spectral sequence that is underlying it. So you can get into some very interesting applications this way.
Is all this previous results about this Ligroups, is it also works for H space?
Yes.
That's why you're using omega m, right?
Yeah. Yeah. In fact, that's right. This is really the first meaningful H space, right? Beyond Ligroups. Okay. Yeah.
Do you have any